Hello guys, let's start the second part of the exciting automata called non-deterministic finite automata or NFAs. Let's start with introducing a new or let's say a special transition that is strictly prohibited in the DFAs. To introduce this new transition, let's first shine our knowledge. Okay, so the question is, what is the condition for transition from Q9 to Q21? Is it conditional to move from Q9 to Q21? If it is the case, then what is that condition? Yeah, as we learned so far, the input tape, if it contains A and if it sends A to here, that is the condition for transition to 21. Okay, so bottom line is the transition is always conditional, right? So now the question is, what if I remove that condition? As you see, this is a transition that does not have any symbol. In this case, we would say, hey, Q9 and Q21 are short-circuited, right? So the definitions of the short circuit is an edge with no alphabet or no condition. Okay, so if there is no condition, it means that machine can unconditionally move or transit from Q9 to Q21. But the point is that we would need a symbol for that. We cannot leave it blank here. So the mathematician picked the lambda for the symbol. What? Lambda? We have been using this before for the empty string. Yeah, that's the point. That's true. For the short circuit, they picked the lambda as well. Because of this symbol, this kind of transitions is called lambda transition. And as you will see, it has a very important role in automata theory. We will go over that later. Now, how we can digest this? Lambda was for empty string. Now it is for short circuit. Yeah, there is some justification here, and I want to mention that when we were introducing lambda for the empty string, we said 0 or no symbol, and exactly now we have 0 or no symbol here. That's probably the reason that they picked this lambda for the short circuit. And be careful about this. Using the lambda for these two different purposes, sometimes they're a little bit confusing, but you will get used to it, right? Especially when we said, hey, lambda cannot be used for the alphabet, right? It is prohibited to be alphabet. And right now, you should not consider this as an alphabet. It is still just a symbol. Let's officially define what is lambda transition. Lambda transition in automata theory, so as you see, automata theory, it means that it is extendable to other machines as well, is a transition that machine can unconditionally transit. And as you will see later, this lambda transition will change our view about the subrules. Let me take some examples to show you how it is possible. Look at this transition. We have A here, we have lambda here, and the question is, what is the delta of Q3A? Machine is in Q3 and it reads A here. What is the response for this? Based on our knowledge so far, definitely Q3A is Q9. But since we have a lambda transition here, which is a short circuit between Q9 and Q21, it means that if machine is here, it unconditionally can jump to here. So it means that it is not only the Q9, but also it can be Q21 as well. So we have two response here, and the range will be Q9 or Q21. Okay? Now let me take an example. Write the transition function of the following transition graph. All right, let's start from the Q0A and see what is that. Q0A will be Q1, and since again we have lambda transition here, Q1 and Q2 are short-circuited, and it can be Q2 as well. How about Q0 and B? For Q0, we don't have any transition for the B, so it will be empty. And you can continue this, right? The point was using this lambda, all right? If you continue whatever we did so far, we will get this transition function. And from now on, if we have empty here, you may eliminate them. So the final transition function, the algebraic notation of the transition function, it looks like this. So if you don't have any subrule here, it means that it was empty and we eliminated that. Now the question is how NFAs behave when we have such things. Let me ask this question. When machine encounters two things here, what would be the behavior of the NFA? We don't need to define a new one. We already know that if machine has multiple choices, then machine starts parallel processing. This is not a new behavior. We already know that. Okay, now I want to take another example to show you that in some cases we have different situations. In the previous slide, we had A and lambda, and now we have lambda and A here. And let's see what is the difference. And the question is, what is the delta of Q3 and A? If you look at this, there is no outgoing transition for A here, but Q3 and Q9 are short-circuited. Okay, so machine can jump here and see whether there is any transition for A, and we see this. Okay, so what is the Q3A here? It will be Q21. It means that if machine is in Q3 and if the input is A, machine jump to Q21. And this is how this kind of lambda transition works. So I wanted to say by taking this example that it is not the case when you see a lambda transition, then you would say, okay, yeah, we have parallel processing. No, we need to calculate first that what is the result, and then based on that, we need to decide what is happening. To better understand the lambda transitions, let's see them in action. I'm going to take some examples, some machines, some NFAs that has lambda transition, and let's see how they behave. All right. Okay, so for this machine, the starting configuration is just one symbol in the string, and we are in Q0, and the main process start normally. And we know that how it works. So A will be read and will be sent to Q0. Q0 will calculate Q0A. And based on our knowledge, we know that it is either Q1 or Q2. Why is that? Because Q0A goes to Q1 and Q1 and Q2 are short-circuited, so the machine can jump from Q1 to Q2 as well. So we have multiple values for this subrule. All right. And what is the behavior of the machine when it has two possibilities? We already know parallel processing will start. How? The machine replicates itself with exactly the same current configuration, right? And let's assume that for this process, machine goes to Q1, and for this process, machine goes to Q2. So the A is consumed right now. We already know what does it mean. For this process, we are out of the symbol. Machine had to stop here. And for this machine, we are out of the symbol and machine stops here in Q2. All right. So now it's time to analyze because both of the processes now stopped. Now we need to analyze what is happening here. The process number one, it halted in an accepting state and it is out of the symbol. So all of the condition for accepting this string are satisfied and machine accept A. How about the second process? The second process is out of the symbol. Machine halt, but it halted in an regular state. So this process will reject the string. And overall, we know that since one process accepted it, it will be accepted. So there was actually nothing new here. The only new thing was how we calculate the subrule when we encounter a lambda transition. Yeah, for sure, let's see lambda transition in action for other strings as well. So we have AB right now. So AB, we already know how it behaves for the A. So let's go over it very quickly. So the A will be consumed. We will have two processes and A will be consumed. The bottom line is this. Now we are in this situation. So the end of the clock one or time frame one, we have this situation. So now we need to ask this question, what would be the next time frame? So then in time frame two, B will be sent here into Q1. Then what would happen? Q1 will calculate what? Delta of Q1 and B. Okay, so what is the result for this? Since Q1 doesn't have a B, but it can jump here, so the result will be Q3. And remember that for NFAs, we need to use a set for the range. How about this guy? This guy will calculate Q2 and B, and the result will be Q3. So both of them will calculate, based on this input to Q3. Now what? Now the B will be consumed in the process number one, and the same thing for the process number two. Now we are out of symbol here. Machine has to stop here, and we are out of symbol here, and machine has to stop here, right? And in this situation, both of them are in the accepting state. So process number one accept it. Process number two will accept it. Overall, the string will be accepted. Now, let's take some examples about some more interesting machines. So look at this machine, Q0. We have lambda to Q1 and Q2 here. And we have a lambda here. So this is definitely a better example to understand how the lambda transition works. For this string BA, the B will be read and will be sent to Q0. Then Q0 will calculate what? Q0B. Okay, and based on our understanding so far, since Q0 doesn't have B, it jumps here and then it calculates Q2. How about this way? It jumps here and there is a B here, so it is Q3, right? So we will have multi-value Q2 and Q3. Since machine has two possibilities, then machine start parallel processing. How? It will replicate itself, the same configuration. So let's assume that the process number one goes this way and the process number two goes this way. All right, so B is consumed so far. Now what? Now A will be sent to Q2 here, and A will be sent to Q3 here. And then Q2 and Q3 needs to calculate this. So Q2 and A, and here it needs to calculate Q3 and A. Let's see what is the response of each one. This guy will calculate as Q2 because we have an outgoing for A. How about this guy? This guy doesn't have anything, so it will calculate as an empty. Process number one will consume A, but process number two cannot consume A because there was no transition for Q3A, right? And since there is no transition, process number two will stop while all of the symbols are not consumed. And how about this one? This guy will stop because it is out of symbol. So both of them has to halt for two different reasons. The process number one will accept this because it is out of symbol. It halted in an accepting state, right? So definitely it will accept the string. But how about this guy? Even though it halted in an accepting state, but the symbols are not consumed. So this guy needs to reject it. And what would be the result for overall? It will be accepted because at least one process accepted the string. Here we have an exercise for you guys to the same machine but different strings. But remember that it is not the case that we always have two processes at the same time. Yeah, so if we had something like this, and then the machine had to create three processes, right? Yeah, this is keeping your mind. Now let's see how we can define mathematically the NFAs machines. For the DFAs, you remember the transition function looked like this. The Q or the range was only one value, but now we can have several values or even no values. That's why we decided to use a set for the range, right? So now the question is, how can I change this definition in such a way that it can accommodate a values like this or this or this? These are actually a subset of the Q, right? So how can I represent the range in such a way that it can have all possible subset of the Q? Okay, so you need to use your knowledge about the set theory. We need to use the power set. We know that the power set that we denoted with this notation, it can have all of the subsets of the Q. And in the range, since we need to have one of those, so the power set is the best way to represent this transition function, right? So this will be our transition function definition for NFAs. Just very quickly, let me review what we are talking about. For the DFAs, the subrules look like this, and the transition function rule looks like this. But for NFAs, we have such things. Actually, we have different other things, but for now, since we just learned the lambda transition, so the subrules look like this, and we change the transition function rule to this one. So the domain is the same as the DFAs, but the range is 2 to the q, which is the power set of the q. With this being said, now let's formally define the NFA. NFAs will be defined by the same quintuple that we learned for the DFAs, exactly the same. The only difference is this transition function that we just defined in the previous slide. So the Q, sigma, and Q0 and F are the same, and we just define this guy. All right. Now let me ask this question. What kind of function is this? Is this a total function or a partial function? Yeah, you will see it is total function. I am sure that you will ask yourself why it is still total function. Yeah, we will see through some examples. But yeah, let me one more time to emphasize that everything is the same as DFAs, except for the transition functions that it has this small difference here. Okay, now let me take some example to show you that why delta is total function. Just write the transition function in algebraic notation. We will see such thing, right? And now I ask you to draw the Venn diagram of this delta. The Venn diagram looks like this. So we put all of the possible subsets of the Q here. These are all of the subset of the Q, and the domains is the same as the DFAs. And as you see, there is a mapping between all of the domain members. So for example, for this guy, even though we don't have any transition, but based on this definition, it is pointing to the empty, right? So it means that all of the domain members are defined. So what is the meaning of this? It means that type of the function is total function. So now let me summarize NFAs versus DFAs. The transition function looks like this. The examples for the subrules look like this. Type of the function, both of them are total function. Type of the processing, NFAs, has this ability of parallel processing, but DFAs are always single processing. How about the associated language to NFAs? Yeah, let me take some examples. How can we analyze this machine and figure out what would be the associated language for this machine? So we need to collect all of the strings that this machine can accept. All right. Definitely, if we put A here, it goes here and it stops here. So A will be accepted here. What else we can put? Do you agree that if I put AA, this will be accepted as well? So how come? So if you put AA, A goes here, and since the Q1 and Q2 are short-circuited, machine can unconditionally jump to here, and when the machine reads another A here, it goes here and will be accepted. So A and AA will be the associated language to this machine. How about this one? What is the associated language to this machine? We know that A, B will go here and will be accepted. So one string will be AB. And since machine is here, it can jump here because it's a short circuit. Again, we have another short circuit and machine goes here. All right. So it means that if I have another AB, it will be accepted as well. So AB will be accepted. And because of this reasoning, AB will be accepted as well. So the pattern now is really clear. So it means that the pattern will be AB to the N in such a way that N greater than or equal to what? To 1, because at least it should be 1AB. And since the lambda is not accepted, so it should be greater than or equal to 1. So this will be the associated language to this machine. In this example, we are gonna design a DFA and NFA with two states. So we have a limitation for the number of the states. For the following language over A and B, the set of all the strings that ends with A. Okay, so let's first we specify this formal language with a set builder, the set of all the strings that ends with A. So before it, we can have anything, but it needs to end with an A. So the A is constant. We need to define W here. And W can be anything. And you know that when we say anything, it belongs to sigma star. So this will be the set builder for this formal language. And now we need to design one DFA and one NFA. Okay, now let's start with DFA. Anything that ends with A. So how can we capture this? So if we see an A here, it might be the last A, right? We send it here and we accept that. Okay. And if there is any number of B's, we can keep the machine here because it's not A, right? So I am trying to capture the last A. When I see one A here, it might be the A that I am looking for. So I send it to here to be accepted. But what if we have more A here? Yeah, we can keep it here because one of them can be the last A that I am looking for. How about if I see a B here? When I am here and when we see a B, it means that, yeah, definitely this is not the string that I am looking for. So I send it back to here to start over. Okay, are we done? Yeah, we need to check. How can we check? For the DFAs, you remember that we have a constraint. Every state needs to have one outgoing transition for every alphabet. So here we have one transition for A, one transition for B. So we are done here. How about here? One transition for A here, one transition for B here. So it means that we are done for the DFA. Cool. Now the question is, how can we design an NFA for the same language? Designing NFA is much easier. How? Yeah, we start from here. Anything W. How can we design an NFA for W? It can be A or B. And then we need A here. Yeah, we go here and we put A here and we will accept that. That's it. This is NFA. And this will accept anything followed by A. How come it works? Yeah, probably you are asking this because anything you put here, let's say, for example, BAA, something like this. Definitely there will be many processes, right? At least one of those processes will consume this BA here, and it will consume this A here, and it reaches here, right? Can you imagine that? We don't need to trace this to make sure that this string will be accepted, right? Because there will be many processes, at least one of them will consume this BA here, and it consume this A here. How about, let's say, for example, A, B, 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 A, something like that. Or maybe we can add something like this, make it bigger than this. So how can I prove that this will be accepted with this machine? I would say exactly the same thing. I don't care how many processes will be created, but I know that at least one of them will consume all of this, which is our W here, and it will send this A to here, right? So you see how easy is designing NFA, and how beautiful is this kind of machine. And when we added this parallel processing, how the machine, it looks like, easier to design, and it will be simpler actually to design, and the transition graph looks like very simpler. I put some exercises for you guys, and I do recommend you go over all of them. One of the most interesting part of this course is the relationship between the machines and the languages. What does it mean? It means that, let's say, this is the set of all machines, any kind of machines that we have learned so far and we will learn in the future. So this is the set of all machines. And here is the set of all formal languages. Okay, now the question is, what is the relationship between these two? What does it mean? Let me clarify exactly. Is this the case that every machine is associated to a language? So in other words, this language is an associated language to this machine, and this one is for this one, and at the same time for this machine, and so forth. Is this the case? Is this the case that every machine is associated to a language? Yes, it is the case. Every machine is associated to a language because we design a machine based on a language. How about the other way around? Is this the case that every language is mapped to a machine? Yeah, we don't know yet. Our knowledge is not enough to claim that. To claim that all of the formal languages, there is a mapping between them and a machine. Now the question is, why should we care about this? Why we are interested in this relationship? Yeah, it's a very important question because later we will see that we can encode every problem into a formal language. So we can convert every problem by encoding to a formal language. In other words, formal language is equivalent to a problem, and machine is the solution. Yeah? So with this new equivalency that I just explained, if the formal language is equivalent to problem and the solution is equivalent to the machine, then yeah, look at this. It means that when we create a machine for a formal language, in fact, we are solving that problem. All right. So that's why we care about this question in computer science. Okay, so now let's rename those two sets with this new equivalency. Instead of the set of the machines, we would say this is the set of all solutions. Instead of the set of the formal languages, these are the set of all problems. Now, this relationship will be very obvious. If I ask the same question again, is this the case that every solution is mapped to a problem? Yes, there was a problem that we solved that. Yeah. Now, let me ask the question, the other way around. Is this the case that every problem has a solution? Yeah, that's something that we really don't know. Our knowledge is not enough to respond to that. But, heuristically, you can say, yeah, definitely it is not the case that every problem has a solution here. In this section, we would like to compare DFAs and NFAs. To compare two things, we would need some metrics to be able to compare, right? So what is the matrix for comparing two automata? We use a new concept called power. In fact, we want to know that DFAs and NFAs, which one is more powerful? We need to clarify what's the meaning of power, of course. To understand that what's the meaning of the power, let me ask this question and try to heuristically respond to this question. We have two classes of automata, A and B. The question is, what is the best criteria to state that class A is more powerful than class B? You may pause the video and try to answer this question. After some brainstorming, probably you would say, okay, if class A can solve more problems, then class A is more powerful. And this is the correct answer. If class A can solve more problem, or let's say accept more formal languages, then it is more powerful. Now let me give you the official definition of the power. When we can say class A is more powerful than class B, if the set of the languages that was recognized by class B is a proper subset of those languages that can be recognized by class A, then we would say class A is more powerful than class B. In other words, if the portion of the formal languages that can be recognized by class A is a superset of those portion that can be recognized by class B, then we would say class A is more powerful than class B. Okay, based on this definition, now let's get back to our NFAs versus DFAs. Which one is more powerful? To understand this, the universal set of this question is all of the formal languages. And the question is, what portion of these formal languages can be accepted or recognized by DFAs, and what portion can be recognized by NFAs? If we can specify these two portions, then we can find out that what is the relationship between these portions, and we can respond to that question clearly. To investigate this, let's use these notations. So I am going to use the U as all of the formal languages, which is the universal set of the formal languages. Those portions that can be recognized by the DFAs, let's call them D. And those portions that can be recognized by the NFAs, let's call them N. Now the question is, what is this relationship? We already know that two sets can have 5 different relationships. They are either like this, it means that DFAs can solve this portion, NFAs can solve this portion, and there is no relationship between them. So it means that we have some languages here that can be solved only by DFAs. Do you think that it is correct? Definitely not. So definitely this is not a good relationship between these two portions, right? So we don't agree with this one. How about this? This portion are those formal languages that will be recognized by only DFAs, and this portion for the NFAs. Yeah, it means that again we have some languages like here that can be only solved by DFAs. Again, heuristically, we would say no, that's not the case, right? Okay, so how about this one? The portion that NFAs can recognize is here, and the portion that DFAs can recognize is a superset. So it means that DFAs, in this case, if we prove this, it means that DFAs are more powerful than NFAs. But again, this is not the case, right? Heuristically, we understand that this cannot be true. Okay, so now we remain two things. Either they are equivalent or the portion that can be recognized by DFA is a proper subset of those portions that can be recognized by NFA. So one of these two should be correct. Let's see which one is correct. To investigate which one is correct, we will ask this question. Can NFAs simulate DFAs? What does it mean? It means that if I have a language here, and if I create a DFA for this language, can I always create an NFA for the same language? Always. If this is the case, then I would say, yes, NFAs can simulate DFAs. So whatever DFA can do, it means that NFA can do. Yeah, the answer is yes, but how can we mathematically prove that? One way is to convert a DFA's definition to NFA's definition. What does it mean? Let me take an example and explain everything through an example. Look at this machine. This is an DFA, definitely. We have seen this before. Let's find all of its mathematical definition. I mean, these 5 items. We already did that, right? So the Q is Q0, Q1, Q2, and the alphabet is A and B, and this is the algebraic notation of the transition function. Initial state is Q0, and the set of the final state is just 1. So this is the mathematical definition of this DFA. Now let me ask this question. Consider this now as an NFA. Is it an NFA? Can we consider this as an NFA? Why not? We can consider it as an NFA. Because when we were introducing NFAs, we said, yeah, NFAs can have those 2 violations and it can have the lambda transition, but we didn't say they must have all of those 3 things. So in fact that all of the DFAs can be considered as an NFA, right? If this is the case, then we would say, okay, so what is the mathematical definitions of these 5 items? As you see, we have the same thing, almost the same thing, the Q, the alphabet, the initial state, and the set of the final states. The only difference we see here is a simple difference that all of the ranges are located in a set. If you compare these two, then what you would say? The only difference is this, right? So it means that we can convert any DFA to an NFA. How can we do that? No changes here, no changes here, no changes here, and no changes here. The only change is this guy is just the one value, and here we just have one set instead of that. So it means that if I don't touch the DFA and I just put the range inside a set, then the definition of the DFA will be converted to NFA. So simple, right? That's it. So now we have an algorithm. How can we convert a DFA to NFA? It's so easy. We just need to change these subrules to this subrule. That's it. This is a very simple algorithm, and this can be done for every DFAs. And the rest of those 4 will remain untouched. And just remember always this, that finding an algorithm is actually a mathematical proof. So what is the conclusion? Can NFA simulate DFAs? Definitely. So up to this point, we would say that DFAs are a proper subset of the NFAs. But now we need to ask another question. The other question is the other way around. Can DFAs simulate NFAs? In other words, if I create an NFA for a language here, so let's say it's an NFA, I created for this language, can I convert this to a DFA? So in this way, if I can prove that, then all of the NFAs also are DFAs. The answer is yes, we can do that, but it is not so obvious. Let me take an example to make it a little bit clearer. So we have an NFA here, and the question is, can we convert this definition to a DFA? Yeah, but it's not obvious, and it needs to be covered in a separate video. All right, if this is the case, yeah, theoretically, if we can convert every NFA to DFA, then it means that based on this theorem, DFAs and NFAs are equivalent. So it means that both of them can recognize the same portion of the formal languages. Let's get back to our machines and languages association. So if this is all of the formal languages, this portion of these formal languages can be recognized by DFAs and NFAs, both of them. Okay. And later, when we introduce a new machine, let's say, for example, the class X that we will introduce later, just remember that it needs to be a superset for NFAs and DFAs. It means that it should have backward compatibility. It should accept this portion as well and more. It means that the next generation or the next class of the machines that we will be introducing, they need to be more powerful than the DFAs and NFAs. Okay, I am gonna stop here and see you guys in the next lecture.